Problem 27. The probability density function of the random variable x is defined as given. What is the maximum likelihood estimate of the parameter lambda based on two independent observations, x equals 1/4, x2 equals 9/16? So problem 27, we're given a density. We want to find the maximum likelihood estimate of this density given that our x values are this. Now, since x1 and x2 are independent, it's just a product of those individual densities. And the likelihood can be rewritten as this, which is, we think of it, it's really as this joint density is a function of x's. Here, the likelihood we think of that the lambda is the variable and the data are fixed, and we're going to find the value that maximizes that. So we get this value. We plug in our x1 and x2, simplify it, and we get this. Now we need to take the derivative of that. The derivative of this, which is this, we set it to 0, implies lambda is equal to -3. Problem 28. The probability density function of a random variable x is defined by f of x equal 1/2x and 0 elsewhere. What is the probability that one of the two independent observations of x is less than 1 and the other is greater than 1? So problem 28, we're given a random variable x is defined with a certain density. So what is the probability that one of two independent observations of x is less than or equal to the other? So the probability that x is greater than 1 is this. So if the probability of being greater than 1 is 1/2, then the probability of being less than 1/2 is 1/2. So there's two possibilities. We can have x1 less than 1 and x2 greater than 1, or we could have x1 greater than 1 or x2 less than 1. Well, those are independent, so it can be rewritten like this. Those are independent, so it can be their product. And we know this probability, so it's 1/2. Problem 29. A certain large university, the weights of male students and female students are approximately normally distributed with means and standard deviations that are shown there respectively. If a male and female are selected at random, what is the probability that the sum of their weights is less than 280? So problem 29. So here, male students are distributed this way, female are distributed this way. We're asked to find something about their sum. So if we let y equal the sum of the male weights plus the female weights, it can be shown that that's also normally distributed with the means added, and this would be the standard deviation. So it's the variance is added, divided, or over under the square root sign. So plug in the values that we know, then it's normally distributed this way. So to find the probability that we're less than 280, we subtract the mean of both sides, divided by the standard deviation, and that is a z value. And then that is equal to minus 1.2. Looking it up in a z table, we get 0.1151. Problem 30. Assume the observations from the random variable x is equal to 1 and the probability x and distributed with density function e to the minus x with probability 1 minus p. What is the moment generating function of x? So problem 30, we're asked to find the moment generating function of x. Well, x, they said, takes on the value 1 with probability p, and it takes on this density with probability 1 minus p. So the moment generating function is the expected value of e to the tx. So this is a Laplace transformation. So this expected value is over each possibility. So it's e to the tx times p plus 1 minus that integrated over the density. So here, if we for this, I make a u substitution and bring this down, and that simplifies to this, plug in the limits of integration, we get this, and that's one of the answers. Problem 31. 5 observations are drawn from a population with an unknown continuous distribution. The least and greatest observations are to be used as a confidence interval for the median of the population. What is the probability that the least and greatest observations bracket the median? Now, problem 31, we have 5 observations. And what's probably that the least and greatest observations bracket the median? Okay, so notice here that for each xi, the probability that we're greater than the median is a half. That's the definition of the median. And this case, for the probability that we're less than the median is also a half. Okay, so and then case 3 is that we have some less than the median, some greater than the median. So these are the only possibilities that can happen. So the probability that they're all greater than the median is that. So, well, if we add each of these probabilities, it has to be 1. So 1 equals, now the probability of this case that they're all greater than the median is be written like this, plus the probability that they're all less than the median can be rewritten like this, and then the plus probability that some are above and some are below. Well, this piece, they're all less than the median, is 1/2 raised to the 5th. This, that they're all greater than or less than the median, is 1/2 to the 5th, plus, and then we don't know this, probably that some are above and some are below. Well, then take those to the other sides and it leaves this, and the answer is 15/16. Problem 32. A coin with probability P of heads is tossed independently n times. Let xi equal 1 if the ith toss results in a head, and let xi equal 0 if the ith toss is a tail. What is the expected value of x1 times x2 ... all the way to xn? Question 32. What is the expected value of x1 times x2 times all the way to xn? So let's look at the individual expectations. So the expectation of one of the x's is you sum over all possible values of x times the probability of that x, which is 0 times 1 minus p plus 1 times p, which is p. So the expectation of this product is this. the pi symbol from 1 to n of xi. That means multiplied, and that's what that is. This expectation can go into the product. Well, we know the expectation of any xi, which is p, and then the product p n times is p to the n. Problem 33. Let x1 through xn be a random sample from a normal distribution with density function given. Using the Neyman Pearson lemma, determine a critical region to test the null hypothesis, mu is 0 and lambda is 3 against the alternative hypothesis that mu is 2, lambda is 3. So question 33 is, well, we know that we want to reject the null when this is happened. So the alternative density is much larger than the null. Well, how large? We need to find the k that makes this, 0.05. So the joint density is, since those are all independent, we take the product of one of them, and then that can be rewritten as this. Now, but this, I didn't plug in any values for mu yet, or lambda. So we know this has to happen. So k, and this has to be greater than k. So this is the alternative hypothesis, which means mu is 2 and lambda is 3. So you plug in those values. And here, mu is 0, lambda is 3. So it simplifies to this. Then if we take the log of both sides here and here, we get this. Now we need to divide by -3, which then changes the sign. And we're going to call this some constant c. So the answer is this has to be less than c. But this wasn't one of the answers. So, but if you take both sides times -1, it switches this order. Or if you subtract that over and subtract this over, then you get this, which is one of the answers. Problem 34. The correlation coefficient from the n pairs of data may be affected when each xy is replaced by which of the following values? So 34 is which of those affects the sample correlation coefficient. Notice that if you add the same quantity to each x, it affects the mean the same way. So you're subtracting a constant addition or subtraction. So adding a value to each doesn't. Multiplying the same value doesn't affect, because if it's the same value c, then it's going to be c squared here, and c to the 4th square root, c squared, they're going to cancel. And switching x and y clearly doesn't affect this. So the answer is E. Changing one of the variables to negative is going to affect the sample correlation coefficient.